few videos ago, we were talking about research questions and how they should be falsifiable in order to be within the domain of science. So any research question should, in principle, be possible to be falsified through observation or through data. And that very much linked to this quote here: the absence of evidence is not evidence of the absence. So the fact that in our sample we do not observe an effect, or we cannot claim with confidence that there is an effect, that doesn't mean that there is none. It just means we did not observe it. Or technically speaking, it is evidence that there's no effect, but it's not proof that there is none. And the hypothesis testing framework, what we have seen so far of the null hypothesis, the alternative, p-values, reject, do not reject, etc., it allows us to reject the null hypothesis in favor of the alternative. But if we fail to reject, again, that does not mean that we accept the null hypothesis. So if we do not reject it, still we do not accept. And this is very much the same. If we do not have evidence that there is an effect, that doesn't mean that there's none. We just do not have enough evidence. Normally, we do not have enough statistical power. And so the effect, if it really exists, if it's present in the population, it's just too small to be detected in our current setting. Because we don't have enough data, because there's too much variation anyway, or because, again, it's very small. Maybe there's no effect, or maybe there is some, but too small. We don't know. The point is, if we do not reject the null hypothesis again, it doesn't mean we accept it. Maybe there's effect, maybe there's not. We don't know. And so we cannot test through this framework hypothesis about the absence of an effect. We can't. So we cannot test something like alternative hypothesis, there is no effect, and null hypothesis, there is an effect. This is not what we test. And of course, again, if we're testing the typical H0, no effect, and then H1 effect, we never accept the null hypothesis. We either reject it or fail to reject it. If we really want to test something like the absence of an effect, then there's something called equivalence testing, and it's essentially in the direction of testing whether the effect is sufficiently small, so whether it's contained within certain boundaries that we arbitrarily set to be too small or irrelevant in our case. Always, we have to keep the assumptions in mind, because ultimately the p-value is computed from the test, and the test makes different assumptions. And those assumptions are normally false by definition, like we said. We do not have exactly Gaussian distributions, for example. We do not have symmetric distributions. Many times we do not have really random samples. So at some point you have to start wondering which test should we use. Because if we get very picky, our data doesn't mean the assumptions of any test. Now what matters is how reasonable those assumptions are. It's not whether our data is Gaussian or not, it's about how much it looks like a Gaussian distribution, and especially around the extremes, which is what we're testing anyway. So we have to be reasonable and a little bit flexible about this, not just, be very picky and say, no, it's not Gaussian and that's it. Well, maybe it's close to Gaussian and it's good enough. The p-values are, to some degree, approximated because those assumptions are not met. So why use any arbitrary threshold alpha? Why use a 5% or a 1% if we know that to begin with, there is a certain amount of error in p? P is just estimated, so why be so picky about p 5% or 502% or 4.9%? What we can do is run different tests under different assumptions and compare their p-values. If they tend to disagree, then we should take a closer look at the data, knowing or keeping in mind these assumptions to try and understand better what's going on in our dataset. And we should always look beyond just the current study. So look at past data, look at future data if you can, collect more data. Not just look at the one sample you have, but think about the whole problem holistically. Look at previous hypotheses, previous studies, etc. And then something to keep in mind as well is that all these tests, and ultimately when we talk about regression, we will see that we build models. Everything is based on some kind of model. So do not let the model assumptions limit the kinds of questions you ask to your data. I've seen many times that someone has data it doesn't look so much Gaussian, so they're going to try and test something else, or they're not going to control for other factors because it doesn't look like Gaussian. Well, if you ask me, do it, but just keep in mind that you're making a certain assumption. And, in the end, it's not really about having a p-value close to 5% or just under 5% or just over 5%. It's about, in qualitative terms, where are you? Is it an 80% p-value? Is it a 0.00002 p-value? Well, that's what we have to think about. And we're going to learn a lot more if we actually explore the data and through that exploration refine our questions. So refine our hypothesis. What are we actually going to test? Only after finding the right questions, it makes sense to start doing inferential statistics. So what we're going to see is that by exploring the data, trying to find more patterns, more possible interactions, factors that we have to control for, etc., then it makes sense to build a model on top of that to try and do inferential statistics and test actual hypotheses, not just collect data, run some t-test, and that's it. Now, our analysis models should exploit the structure of our experiment. We are not just testing what is the effect of one independent variable on a dependent variable, so something like differences in the dependent variable across groups in an independent variable. It's about testing that while controlling for the other things, taking all these other factors into account. Only by doing that, we're going to be able to provide meaningful answers to our research questions. It's not just about testing A versus B, it's A versus B, controlling for the other things. And meaningful answers very rarely have a yes-no answer. It's always an it depends. So it's not that there is an effect or A is better than B. How much and under what conditions do we have a specific interaction with something else that tells us that in this specific case, you should not do A, you should do B. That's a more proper answer to a research question. And so if you want to put it in one sentence, it could be something like this. The p-value was always meant to be a detective, not a judge. It's always meant to be something that help us or guide us into our research, into our questions in a certain direction. It's not meant to be a judge saying yes or no. It's about pointing us in the right direction during our research, not just yes, no, but where. And ultimately, it's all about replication. If you think about it, the hypothesis testing framework only makes sense in the long run with replications because we have this alpha probability of error or beta probability of error. Given just the one sample in our data set, we don't know anything about whether we are making an error or not. So the p-value tells us something only about our data, how extreme it is. It doesn't tell anything about the population. And we might be making a type 1 error or a type 2 error, we don't know. What is the best thing we could do? Replicate our experiment, our study, and see what distributions of p-values we have. Do we consistently have small p-values? Then, okay, we are even more confident. Do we have a large variation of p-values? Then we don't know. Maybe we just got lucky in the first case. And so, regardless of how much data we have to think about replicating. In a dataset-based research, we hardly ever replicate. When we are just given one data set and we're asked to look into it and try to find connections and try to answer some research question, the point is we are stuck to the one data set. That's it. And we use it over and over and over again to test one hypothesis, another one. And we should not do this because in the end, what we're going to end up doing is just testing hypotheses that are suggested by our data. And eventually we're going to get a positive result. We're going to have a small p-value. But it's just because we are testing something very much specific of our sample. And so if we keep looking for effects into the same data, eventually we're going to find something spurious. As I said in another video, if we strangle the data long enough, it's going to confess anything. So we need to acknowledge the limitations of having just one sample. The p-value again is concerned only with the one sample. Regardless of how large that sample is, it's only one. We should look into more samples, replicate our studies. What is the problem nowadays? Well, that if we have a study with a p larger than alpha, it's not published because we do not have enough evidence to support rejecting the null hypothesis. And then this research is taken as false, or should I say the research question is taken as false. But maybe it's just a type 2 error. Maybe we didn't have enough statistical power. And replication is not rewarded. If you try to replicate the study to have even more confidence, we as a research community, that the result is positive, then it's more likely than not that they don't publish that, or they're not interested in that. But maybe what we think is a positive result is just a type 1 error. Maybe in the original study, we got a type 1 error, and if we do not replicate it, then we're never going to know. And so I just want to give you two quotes here. The new knowledge that we accept in our field is accepted based on single experiments. There's no replication. And so no isolated experiment, however significant in itself, regardless of how much data we got and regardless of how small the p-value, is sufficient for the demonstration of any natural phenomenon. We have to replicate. Maybe we just got lucky that one time. And the null hypothesis significance testing framework is not well understood by senior researchers, let alone juniors. It's, as someone said, the most boneheaded, misguided procedure ever institutionalized in the road to training of science students. We have to keep in mind all these pitfalls of statistical testing, like what the p-value really means, whether we reject the null hypothesis or we fail to reject it but never accept it, how the p-value conflates sample size and effect, etc., etc. Again, just in one sentence that I very much like this, the p-value is just a test of sample size. It's just testing whether we have enough data or not. That's it. It's not testing the magnitude of an effect or whether it's relevant or not. It's just testing, do you have enough data? Do you have a p less than alpha? Yes or no? And if we think back into the errors, well, statistical testing only relates to the random error. That's it. The systematic errors are due to having a bad sample, to bad measurement or measurement instruments, to bad experimental designs. Those are issues normally much larger than statistical significance, than choosing one test or another, or whether I meet the assumptions of one test or the other, whether I'm slightly over alpha or slightly under alpha. These are much higher issues, and they are normally ignored. All we look at all the time is just the p-value and the alpha. But we don't care so much about the experimental design, how we're measuring, how we sample, etc. And so that a measurement is reliable, that we get a p less than alpha, does not mean that it's valid or useful or correct. It just means that whatever you're measuring, we are confident about it. But maybe what you're measuring is not good. Again, in one sentence, what you measure is what you get. And if you're measuring garbage, then you're going to get garbage. A very confident garbage, but garbage anyway.